Alright, so in this video, I want to show you how to fine-tune LLMs on the new AMD Strix Halo. If you've been following this channel, you know that in the past few months, I've had a lot of fun testing and developing toolboxes to make AMD Strix Halo a really solid solution for anybody who wants to create a home AI lab. And I'm sure that you've already been on the Strix Halo Home Lab wiki, and you might even have any of these PCs that include it. These are all mini servers. I myself have the HP Z2 Mini that you might have seen in one of my previous videos, but my favorite one that I use every day and I'm going to use also in this demo is the Framework desktop that was kindly sent to me by Framework, not for a review, but just to experiment and keep developing the toolboxes and documentation to make this useful for generative AI. Now, you know, if you've seen my previous videos, that the software support, the ROCm platform on these specific integrated GPU, inside Strix Halo, has not been fantastic from day one. However, since my first video in August, and we're now today on the 19th of August when I'm recording this, support has improved considerably, and there is a lot of work going on AMD's side to fix some of the leftover bugs and make these even more stable and faster. So I think in the next few months we will see things improve even more. But so far, a lot of the issues that I pointed out in the previous videos have been either, again, ironed out or reduced considerably. And some of the use cases are really fast. For example, we saw some benchmarks and on Llama CPP to run LLMs. Well, since that original video in August, Llama CPP support and ROCm support has improved so much, and you see that the performance has become really good. And also it's about to improve because some of the Llama CPP developers are receiving Strix Halo framework desktops so that they can experiment and write custom kernels. But the same applies to the toolboxes that I made on image and video generation with Qwen image and one. They were quite slow, and the current new version of the toolbox is twice as fast. And again, with some of the things that are on the horizon, they're probably going to become even faster and more stable. A quick note on the format of this video. Some of my other videos, I have enough time to write the entire script, go over it a million times, make every sentence as short and direct as I possibly can to use as little of your time and to give you as much information in that little time. Now that can take, believe it or not, 10 to 20 hours of work for a video of 20-25 minutes, especially when there are demos and things that I have to do. So I just didn't have the time for this one, which means you get a more natural Donato with his broken English sometimes, and with redundant things, repetitions, and stuff like that. So bear with me, but I really wanted to put this video out to go with the toolbox because a lot of you have been asking and waiting for this. But again, for this video, what I thought I'd show you is my new toolboxes that I've been working on for fine-tuning LLMs on Strix Halo. Specifically, we are going to pick Gemma-3, which is a great family of LLMs for fine-tuning, and we're also going to look at GPT-OSS, and although it is not in the table, this will work as well with Qwen models, for example, Qwen-3. And you see that we'll cover different techniques, fine-tuning the full model, and then using LoRA and different quantizations. So all of this is possible, and the good news is that this is actually simple and stable, especially if you're using my setup. So As usual, for my setup, I use Fedora 42. You can install Fedora 43. I think it's probably out by the time I'm recording this video. Update it as your base operating system, and I do not install the graphical user interface because I don't need it. I just use that as a server and I SSH into it, and that also frees up some memory. And then, as I said in all of my other videos, if you have 128 gigabytes of RAM on Strix Halo, you want all of that memory to be available to the iGPU potentially. So you want to use that unified memory, which means you need to tell Linux via these kernel parameters, specifically these two, that all of that memory should be available, so that you go in the BIOS and set the VRAM to the lowest available value, and then you tell the operating system you can use all of the system memory for the iGPU, and that's how you do it. It works really well, and you really have to do this for some of these use cases, because the static allocation that I think goes up to 96 gigabytes will not be enough to fine tune or to run very large LLMs. So this is my setup. If you're using different Linux distributions, I know that there is a different ways of specifying these kernel parameters, and there is also different ways of running toolboxes, and you're gonna need to investigate how to do that, and some other YouTubers and people have documented how to do that. But again, if you want to follow exactly what I'm doing, I recommend to use this setup. So the first thing we're going to do is to get the toolbox, and here I have the command, and I'm gonna just go into my framework desktop. I SSH'd into it, and I'm gonna run this command. This is gonna go and download my container that I pre-built on Docker Hub, and because I had it already downloaded, it's then gonna create the toolbox out of the container, and we can simply do toolbox, enter Strix Halo LLM fine tuning. So that's step one. There is a little bit of a banner. I do update these toolboxes, but this will show you which version of ROC-M I'm using. I use the versions compiled via the ROC platform. This is something that runs nightly, and so we can get all of these updated versions with the latest fixes. This one is from the 15th of August. Then we have the quick start. This is really easy. The first thing you want to do, the toolbox comes with some notebooks that we're going to use, some Jupyter notebooks under OPT workspace, and you want to create a directory in your home directory, which is outside of the toolbox on your host system, and you want to copy those notebooks in there, and that's the command to do that. And so essentially this creates this fine-tuning workspace folder with all of the notebooks in there, and I think if we take a look at this, you will see the Gemma fine-tuning and GPT-OSS fine-tuning with a little bit of libraries, and some of these folders are here because I have already run some of these tests myself. Once you've created your workspace, you can simply run Jupyter Lab, pointing it to that directory. And that's all you need to do to get the environment up and running. It's this easy. Now, once you run Jupyter Notebooks, you are going to find a link with a token that you can visit. Now, obviously, this is running on localhost on the remote framework desktop, which I have just there. And in order to access it, the easiest way to do this without having to faff around with firewalls is to SSH into the box and forward this port to your computer. And I think I show you how to do this even here. So if you SSH with this command, which I'm going to do now. Just like this. Now that port 888 will be available locally on my computer. And I can simply copy the link with the token, and this is going to be different every time you run the toolbox, and then you can very simply go and access Jupyter notebooks. Now, I am assuming that you might have already seen or used something like Google Colab or Jupyter notebooks, but these are some very easy ways of running these recipes with all the commands in one place. All right, so let's jump straight into this notebook. You will see that I am in the Gemma Finetuning notebook, and I typically like to see the outline. Now, as I said, this will show us recipes to get started with fine-tuning different versions of Gemma-3 with different techniques. We'll see full fine-tuning with all the weights, but then we'll also see LoRA and LoRA with different quantizations. And what's important here, I will not try to explain in too much detail what these do and how to prepare the datasets. I think there is a fantastic tutorial or series of tutorials by Trailis Research, and this is where I learn most of these, so I recommend you take a look at this. Now, the only thing to keep in mind right now on Strix Halo, I haven't been able to use Unsloth, so all the ones that use Unsloth, they might not work yet. I've opened a ticket with Unsloth, and if you know what Unsloth is, it's basically a set of libraries that try to make LLM fine-tuning more memory efficient or faster to run. But again, we're not going to do this. Instead, these notebooks will use the Transformers library, and it will use specifically this library from Hugging Face called TRL, which stands for Transformer Reinforcement Learning. Now, we are not going to be doing reinforcement learning here. If you go on LLM Chronicles, which is my series on my deep dive into how LLMs are actually built and trained, you can learn about all of these terms. And specifically, I think if you really want to understand what's going on under the hood, like what all of these parameters are and stuff like that, just take a look at part 2 and part 3. Specifically, part 3 is essentially what we're doing during training and fine-tuning, so you can understand what a loss function is and what's this optimization process called gradient descent that allows us to change the values of the parameters so that the model approximates what we want it to do. And there are also labs and theory here and all sorts of things about how to evaluate models. I'm not going to cover basically any of these here. This is just a guide to get started on Strix Halo. The other thing to keep in mind is that all of these we do with a maximum length of 512, and all of these techniques have a memory footprint or memory requirement, which I've tried to show in this table. And so typically you want to always do a full fine-tune of all the parameters in the model if you can fit that in memory. But as you can see, for example, we cannot do that with Gemma-3 27 billion simply because we wouldn't have enough memory. Because as you can see here, for example, even Gemma-3 1 billion, this is only 1 billion parameters, actually requires 19 gigabytes of memory. But as we will see, it can require twice as much because this is just the memory that the library allocates to specifically this, but there is other memory that gets used during the process. Now, why does it take that much additional memory? Because the process of fine-tuning requires us to do this gradient descent, which means that for each parameter and for each computation that we do, we have to maintain this list, this tree essentially of all the computations. I think I show it maybe in this notebook here from LLM Chronicles, but basically we need to maintain this computation graph, which for a simple neuron is like this. These are the weights, these are the inputs, and that's the output. And then we have to maintain, what multiplications, what calculations we did, so that we can go and compute what's called the gradient, which then allows us to see how we steer these weights to make the model do what we want to do. But again, for large models, these computation graphs become very big. And then for each weight, we need to store an additional value, which is this derivative or gradient. And that's why this process actually takes a lot of memory. Now, the other techniques like LoRA rank adaptation, and LoRA with different quantizations, as you can see, they reduce the required memory footprint, because you freeze the weights of the model and you add a few weights on top of that. And so you're only fine-tuning or you're only changing and doing these computation graphs for a smaller set of parameters. So that's what we do here. And obviously with the quantization, we've discussed that in previous videos, you can also reduce how much you allocate to each parameter. So all of these modern LLMs are typically released in a format called BrainFloat 16, which basically is 2 bytes per weight. So for example, Gemma-3 1 billion will be 2 gigabytes of memory. Gemma-3 8 billion will take 8 gigabytes. But if you quantize it to 8 bits, so 1 byte, then it will only take 1 gigabyte. And so this allows you to better use the memory. So that's all I wanted to tell you. Let's jump into this notebook. The first cell simply does all of the imports and sets up a few functions. Now, one thing you want to check is that the environment here is set to Python VM. If it is not set to Python VM, you want to go and click that. Otherwise, you will have an error. It will tell you, for example, Torch doesn't exist. Now, this bit here, you can ignore it. This is just a warning because we have Flash Attention library, which has got its own kernels for Flash Attention, and PyTorch, which has got its own kernels. And this is basically Torch telling us, there are different versions. I am actually overriding some of them. I'm picking one version. Then you are going to need to log in into Hugging Face. I have commented these 2 lines, but here you want to put your Hugging Face token and then run the cell. And this is necessary for you to be able to download weights and datasets from Hugging Face. And then we want to select a model. Here for this demo, I'm going to select the 1 billion parameter model. And then we want to set some what are called hyperparameters. Again, go to LLM Chronicles if you want to understand what all of this actually means. But we can use these parameters here, this learning rate, which is also recommended for Gemma. The number of epochs, you typically fine-tune for 1 to 3 epochs, and an epoch is simply how many times you go over the data set, and then the batch size is how many samples from that data set you pick at one time and you feed into the model. You can play with these, but these are kind of like baseline parameters. Now, for fine-tuning, we need to have a data set that we want to fine-tune the model on. And in this particular case, I'm using this English quotes toy data set, and I'm picking 1,000 samples from it. Did I not run some of the cells? Just making sure. Okay, so we take 1,000 samples from this. This is a function to format them in this role user role assistant, which we need. And then we are doing a split, 20% in the test data set and 80% in the training set. So obviously we end up with 800 training samples and 200 test samples. And I have coverage here again of what all of these data sets mean. So what's a split? Actually, I might show you very quickly. If you go through that episode, you typically have a training data set, a validation data set, a testing data set, and they're used for different purposes. Now, once we've got all of these, we can go and take a look at the samples in the data set. And this is basically training the LLM so that it is asked for a quote on certain keywords, and then it responds with a quote. So let's take a look at another one, just randomly the fifth one, for example. Give me a quote about inspirational, and then we want the assistant, the LLM, to respond with one relevant quote. So now let's do full fine tuning. Now, this is what you should aim for. Let me be very clear. If you have enough memory, you want to do full model fine tuning. You don't want to do LoRA. This is going to perform better. Actually, you might find, depending on the task, that, for example, doing a full fine tune of Gemma-3 12 billion will perform better, again, depending on the task, than doing a LoRA quantized fine tune of the larger version. And you need to experiment. Now, to get this going, the first thing that we do, we load the model and the tokenizer for the model. So these are like standard from the Transformers library. One thing to be mindful of is that we want to tell the library to use the eager implementation for attention. You do not want to use for Gemma-3 flash attention during training. This is the recommendation from the official documentation, and I think there are some issues and instabilities with that. Now, as anticipated, the footprint of this model, because we have selected Gemma-3 1 billion, is 2 gigabytes. And then you need to do the supervised fine-tuning configuration. So you need to tell the Hugging Face library what you want to do. And typically you give it a directory where you want everything to be saved, and it will be created here. And inside that directory, the weights and the checkpoints will be saved. And obviously you need to pass the number of epochs, the batch size. We did all of that above, and the learning rate. And you also want to tell it what's the maximum length. Now, I don't remember if I said it before, but just to clarify here, all of these numbers here and memory utilization is for samples up to 512 tokens of size. As that increases, if you have data sets with larger stuff in there, that's going to require more memory, especially when you're using eager memory. So that's something you have to experiment with. For example, it won't be a problem for these models here because you have a lot more memory, but for this one, if you go to like a few thousand tokens, it might simply not fit anymore. All right, so let's go back here. So we now set this up, and then we simply create the supervised fine-tuning trainer with that configuration and the base model, and obviously the training and testing data set. And then we call train, and these things here are just to measure memory, and these will save the model into the folder that we have specified. So if I run this, you will now see the training happening. This will train pretty fast on this Strix Halo. It's a tiny model, and one thing that I like to do is to go to my framework desktop and run AMD GPU top. So this allows me to see the GPU utilization and the amount of memory that's being used. And as I had anticipated and told you, 19 gigabytes is the memory that the library needs to do all of these to load the model and the computations for gradient descent, but the actual amount of memory used is higher because there are other things happening as well in there. So you always want to keep an eye on this, but again, it gives you an idea of how much memory you actually need in order to be able to train these models. Now, you also see that there is a directory, output, full and that's what we created here, and that's the model name. I'm gonna let this train. We are almost finished with the first epoch, and so we're gonna see a training loss and the validation loss from that data set, and this is also saving the model that we trained so far, so that if we were to stop training, we would have this checkpoint that's been saved, and we've basically told it to keep only the last checkpoint for this model. But because of this saving, you will see that some of the memory will spike up because it needs some memory in order to be able to do that. All right, so the model has finished training. This took less than 3 minutes, and you can see the loss that actually went down, at least on the training data set. So some training actually happened, and this has again peak memory around 20 gigabytes. In reality, as we saw, it takes more than that. And then I have this function here that you can call to clean up the memory, because at the moment, when you do this, the memory obviously keeps being occupied and allocated. But if you want to move to the next one, you need to do this to try and free up some of the memory. If you're having issues, you might just want to go in here and restart the kernel. That's going to free up the memory completely. And then as you go to the next one, you should have a clean slate. Now, before we go there, I want to show you, if you go to the index, we can go to Inference. And because we've fine-tuned the model, let's say we want to get this model and actually do inference. So to do that, we are gonna point the model to the directory. So in this case, actually, I should have done this in the notebook. I am adding it here. I think there was model name. Obviously, you could hard code that in here, but this should work. So this is going to load the model from this folder. The tokenizer is going to be that of the original model. You create the pipeline, and then we can actually run this. Obviously, here you can use flash attention, which is going to be faster. The model is loaded in memory, which again doesn't take much memory, and then we basically take one of the samples from the test data set. We apply the chat template, and we simply send that prompt in, and hopefully, did I run this? We should be getting an answer. So we have give me a quote about death and love. And then this is the expected from the test data set. And this is the one that it generated. I can't think of any life that would be more beautiful than the one we have so many times. I'm not really sure what this means, but that's an example. And again, this is the fine-tuned model that we have loaded, and you can go up and you can, for example, change that model up to the 12 billion parameter one. I just want to show you we can do that. And again, in these cases, I recommend restarting the kernel, so that totally frees up all the memory here. And then what you need to do, you do this cell, you select that model, everything stays the same, but obviously the footprint of that model is going to be much larger. I said I expect 8 gigabytes, BF16, 2 bytes per parameter. It's a little bit more as well. This stays the same. I'm going to run it because I want to show you, and again, it creates a new folder with that, but I want to show you already how much we are stretching the memory available, and you can see that the training has now started. Obviously, takes much longer because this model is 12 times bigger. But you can see how with that setting to allow all the unified memory to be used, we can actually train this model and we have some memory left. Now, some of this memory admittedly is used by the operating system, so we can't use all the 128 gigabytes, but this will try to use as much of that memory as possible. I am not going to let this finish, so I'm gonna shut down the kernel and I'm gonna kind of restart it. I'm gonna set the 1 billion parameter model, and what I want to show you, we reload the data set. Just do this again. Oh, fortunately, this, again, you need to choose this Python VM. It should choose it by default. I was sure that it would choose it by default. I don't know why it changed it. But anyway, you stop here, and then we can go, for example, to LoRA. I won't tell you much about LoRA other than, so I think I have this image here from the towardsdatascience.com website, which does explain what's happening. So if this is the original weight matrix, one of the many weights in the layers of the LLM, you freeze these parameters, so all of those we don't touch, and instead you add additional parameters, 2 matrices per original matrix, but obviously these are much smaller. This R is the rank. This would be a rank 2 matrix that you can add on top of this, and so you can do this multiplication. And so these A and B, they are the trainable parameters, and this allows you to still steer the model, but using much less memory, because the computation graph and derivatives and the gradient is much less. So to set that, we load the model, and then we have to create a LoRA configuration, and we have to say again the rank, which would be, just to clarify, this is the rank, so there would be 16 of these, and that rank can be larger or smaller. You could have 8, 32, but again 16 is what people typically tend to use. The larger the rank, the more you're going to be able to manipulate and steer the model, but obviously the more memory is gonna be required. So you need to experiment with that. And the LoRA alpha is just the influence of this rank matrix. It's just a scaling factor. And this is to which matrices, to which of these original matrices that are in the model, that particular low rank adapter, those particular low rank adapters are applied, and these are the Q, K, and V and O projections. I mean, these are for attention, and these are like the feed forward multi-layer perceptrons. If what I'm saying makes no sense, you already know what I'm going to say. LLM Chronicles, all of these is going to be explained in detail there, but obviously you can ignore that or ask ChatGPT. So we're going to do this. We run the cell, and what you're going to see is that the LoRA, so this get PEFT model, performance efficient fine tuning, that's what PEFT stands for. We pass it the configuration and the model, and what this is going to do, it's going to freeze most of the weights in that model, and it's going to just add these, and these 13 million parameters. They are on top of the base parameters of the model. There is 1.3%, and they will be essentially these green ones over here that we're going to be training. So that's essentially what this is doing automatically for us. And then we can simply pass exactly the same as before and press enter, and this is going to start the fine tuning. Now you will notice that this will be obviously faster. We are training essentially 13 million rather than billions of parameters. And if we look at the memory footprint, this will be less than before, even at peak. And the bigger, and obviously to see the full impact of this, the bigger the model is, the bigger that difference in how much memory you would have needed, you're going to see here, because for example, for Gemma-3 12 billion, this is only going to require around 60 gigabytes of memory, whereas with the full fine tuning that would have required 115 gigabytes. And this is where, you know, the larger the model, the more we can see this. So and it's already done the first epoch, and now it's gonna do the second epoch, and I'll see you in a second. All right, so this trained really fast, less than 2 minutes. We can see the loss going down. Now you will see from before, I don't know if I still have it, I cancelled it, you can't see this, but like obviously the loss doesn't go down as much, it doesn't train as well, but it still trains and it uses less memory. And now if you go to the index and you look at the inference, you're not going to use this for the inference, but you are going to use this one, because you need to load the parameter efficient fine-tuning model. So you can't just do it using these, you need to use a different way of loading that. And as usual, you point it to the directory. In our case, the directory will be called output Gemma-3 1B LoRA. So, and just now gonna manually copy and paste it in there. And as usual, you can load it with flash attention. And if I do this, that model, again, the base model gets loaded in memory. The LoRA adapters that we trained get applied to that model. So again, these will be identical to the base model, and these are the bits that we trained, and they get applied and loaded in memory. And so we can see, again, give me a quote about humor and sadness. This is what we expect, and this is what we get. Again, this is not a mistake. This is just the example that was in the training data set, and this is what the model actually generates. So this kind of works for us, and it's got exactly also like the format. I didn't say that before, but the model has also learned exactly the format that we want this in, the quote, dash, and the name. So that's how this is. And again, you can go inside here and you can see that what we have in here are the adapter models in safe tensors format. So these are the parameters that we train rather than having trained the full model. Now, if you go to the index, you can do all of these, but like adding quantization, 8-bit quantization. Let me just restart. Again, I always restart because I want to clean this memory properly. And when I restart, you always rerun the cell with all of the imports, the selection of the model, setting the parameters, and loading the data set. But you stop there, obviously, and then you can jump to this. Now, what this does, it's going to do LoRA, but the base model will be quantized and loaded in 8 bits using Hugging Face bits and bytes library. And this means that obviously it will take the model part will take half the size, and that means that the memory used will be smaller, so you lose a little bit of precision, but you will be able to train a model that's larger with that. And again, so if you see up here, you go, for example, from 15 gigabytes required to 13 gigabytes, and that's good. So, and I think here, obviously this is an error. This will not work like this. I don't know why it says 32 gigabytes. I'm actually going to try and change that in there. Obviously, this would take much more memory. Actually, this will to train these on 8-bit plus LoRa, it will still take almost all the memory you have available, and it might fail. But I don't want to confuse you. But again, what we're going to do here, we are going to use bits and bytes to say, I want to load an 8-bit quantization of the model. And then this is the same LoRa configuration as before. And if we run this, I think what I want you to see is that the memory footprint of this model will be smaller. than before. Actually, not as much smaller as I expected, but it is small. Again, you're going to see more of these things, more of these benefits as we go up with sizes of the model. But again, we can then, as before, we can run that training and it's going to take less memory. I'm not going to run this for you, but maybe what I'm going to show you is the final one, and this uses the least amount of memory, because here you are not just quantizing the model, you are also quantizing the LoRa adapters. So you are making both the precision of these and the precisions of the adapter much smaller, and that's what realistically you're going to need to use to train Gemma 27 billion. And here we are pushing these to 4-bit quantization. And again, both the everything will be in this quantization. And actually, let me restart this kernel and I will show you these in practice. So reloading everything until the first one, and then from here I can just load these and you will see the very reduced memory actually, sorry, mistake. We want to, so we restart the kernel, we load all of these again, and I just want to show you us choosing Gemma 27 billion. We do the data set, and then we can go directly here, loading that model in 4-bit quantization, and we can just go and take a look at how much that takes in memory. Let's give this a second. But again, this is to show you that you can fine-tune with some trade-offs for precision, even a 27 billion parameter model from this, and that's the weight footprint. And then you can just start the training as before. And as I always say, I like to monitor the actual memory utilization of these. And there it is. It's now training. Now, this does take a lot of time. Even if these matrices are smaller, there are many of them because of the number of weights and the number of matrices in this model. And I also think, I am not 100% sure, I need to check, but I also think that maybe some of these 4-bit operations might be slower actually on the hardware than the 16-bit, the brain float 16 format. But again, I just want to show you it is possible to train with some adjustments for precision, also Gemma-3 27 billion. And if you go up here, there is nothing that should stop you from, for example, training with Qwen-3 4 billion or some of the other Qwen models, provided they fit in memory. Alright, so to finish this video, I thought I would also show you how to fine-tune on top of Gemma-3, Qwen and stuff like that, also GPT-OSS-20 billion. It will be very similar, but there are a few differences because this is a mixture of expert model, and that doesn't really affect much what we do, but it comes in this XFP4. It's a 4-bit format for the weights, and on GFX 1151, which is Strix Halo, we can't use this natively. So in order to do the fine tuning, we have to dequantize that model. Now, this is very simple to do actually. And I'm going to show you how to fine tune these exactly as we did before on this toy English quotes dataset, but then also on a reasoning dataset, because this is a reasoning model. So we get started with the same imports as before. I'm not going to say much about these. And again, the other thing to keep in mind, I keep saying that make sure that you select Python VM here. If you don't do that, there might be some confusion and you might try to use a different Python environment which doesn't have the libraries installed. Then we select the model and we set the parameters for learning rate, epoch, and batch size. Then we load the data set. It says not defined. Did I actually run all of this? Okay, so we now have exactly as before. I'm not going to say anything about these. The only difference is that before loading this model, we are gonna create this MXFP4 configuration to dequantize these 4-bit weights into BrainFloat 16 so that we can actually work with them on the iGPU during training. So this will then obviously mean that it's going to take a lot of space in memory. And the LoRA configuration, I've taken this from the official OpenAI documentation, but basically we need to tell the LoRA configuration where to apply those matrices. Again, what we're doing here, and by the way, we're not doing full parameter training because we don't have enough memory, because once you blow up those 20 billion parameters into BrainFloat 16, you'd be in a very similar situation as this Gemma-3 and you just won't have enough memory. So you have to do this if you want to train the model, unfortunately. So you have to trade some of the precision in your training. Now, these are the names of the kind of parameters that we're targeting. They come directly from OpenAI, and we just do this. The model is loaded in memory for us, and then we are going to see, as usual, if we go here, we can see stuff being loaded in memory. And there are 20 billion parameters and only 15 million of them with this configuration are actually trained. We probably want more, but I don't know if I'm doing something wrong. I also think that this rank 8, you can go to like something like 16 as we had here. I think that that's also going to work. So remember, here we had rank 16 here and 32. I think that's probably going to work well. But again, I don't remember, but I think I took these numbers directly from an OpenAI example, but you can experiment with it. And obviously, if you go from 8 to 16, you are going to have twice as many parameters to train there. And then this is exactly the same as before. We create the configuration, the trainer, and then we run train, and that starts training the model. That's actually very, very simple. And you can see, know why my GPU, AMD GPU top was screwed up, but again, you can see how much memory this requires and why we really need to do this with LoRA. We wouldn't have enough memory to do the full training, and this would just crash. And that's gonna take around half an hour. Now I'm gonna shut down this kernel, and I'm gonna start again because I want to show you. Again, we do the first cell, model selection, loading the data set, but instead of doing the non-reasoning data set, obviously you can train these on a reasoning data set. To be honest, you could probably train other models, obviously, on reasoning data sets, but it makes sense to use a model that's already fine-tuned for reasoning. And here we're going to take the multilingual thinking reasoning data set from Hugging Face, which comes with questions and examples of reasoning traces or chains of thought that the LLM can use. If you want to understand more about these reasoning LLMs, they are just normal LLMs, but I think if you go on LLM Chronicles, you want to look at how to build reasoning LLMs. This episode will really tell you everything which is involved into making one of these. But essentially, in a nutshell, you need the LLM to train on reasoning traces. And this dataset contains thinking traces, not for all the samples. I think I have here one where I actually extract the thinking samples, and you can see in here, maybe if I can find it, or maybe I'm not going to be able to find that easily, that there will be a user question, and then there will be an assistant with its thinking trace, and I think there it is. So role, assistant, thinking, and then the model will be trained on this chain of thought in French. That's what the kind of multilingual thinking is here. And then that's what it's going to learn. Now, this is the JSON format. That's just a format, but the model has its own templates. Every model has its own templates with the tokens that say the start and the end of a message or a role. GPT-OSS uses this harmony format, which you can go and check on GitHub. But basically, these start, message, channel, and these are all special tokens that the LLM has been already fine-tuned on that allow it, for example, to distinguish different roles: start, user, message. This is now a user message, and that's the end of it. Start, assistant, that's what we produce as a response. But then the assistant can have channels, and there are channels for thinking, which they call analysis, and that's where the thinking trace would end up being. And then there are channels for commentary, there are channels for calling tools, for function calling, and so on. And then there is obviously a channel for the final message. So you don't have to worry too much about this, because all of this is done by the tokenizer behind the scene to the dataset using the apply chat template. But in case you wanted to see it, this thing here, it would be fed into the model for next word prediction like this. So that system messaging here and stuff like that, they would be just put there with these special tokens, and then you will be able to see the assistant start, the channel analysis, and that chain of thought would end up here. So that was the chain of thought that I think we saw here in this thinking, d'accord, l'utilisor. I don't know, like I don't speak French, but that's where it goes. And then the channel for the final message that will be displayed to the user. So this all happens behind the scene. And once you've got the training data set, this is exactly the same. You run this and then you run the training. And that will happen for us. Hopefully the model gets loaded in memory. These are the trainable parameters. And if we go and look at the memory, that's obviously what's going on. And we already know that this is gonna go up to 80, 90. And you see the memory here is even larger, because some of the inputs here, and that's when I say the context, some of these inputs are quite long. And so for the attention is quadratic in its use of memory, and that means that longer traces will actually require more and more memory to train the LLM on. So it is not just the weights and the again the computation of the gradient descent, but it is also the computation of the attention that's going to take a lot of space. I'm going to let this train. Probably not going to show you the result, because this is going to train very slowly, but ultimately it will train. So I'm going to alt this. So that's all for this episode. Thank you very much. This was a little bit of a different episode, because I honestly have been very busy, but that meant I didn't have time, like I did in most of my other episodes, to actually write a script and to go through each and every sentence and try to make it as tight and short and clear as possible. So I'm sure that I've done a lot of rambling and I've repeated myself a lot of times. So bear with me, but I wanted this video to go out together with the Toolbox because it's going to allow everybody who owns one of these boxes to start experimenting with fine-tuning models locally. As usual, you are on YouTube, so play the game and like the video. Let me know in the comments if this works for you, if you've tried to fine-tune other models. I think you could get GPT-OSS-20B to fine-tune here, but you're going to need to quantize the weights to 4-bit. So you're going to do QLoRA as we did for Gemma-3 27 billion, but I think that's possible. Let me know if you manage to do that. And again, that's all from me.